Okay, so now we're going to finish chapter 8, and you can see that we have gotten all the way down here to anti-dihydroxylation, syn-dihydroxylation, oxidative cleavage, predicting the products of an addition reaction, and synthesis strategy. And these 13 and 14 are going to be very closely related. So we're almost finished. So, anti-dihydroxylation. So dihydroxylation is simply putting two hydroxyl groups across a double bond. So here is, one way that is done. There are many, many different synthetic routes to achieving this, but one way would be to synthesize an epoxide and then open up your three-membered ring using water and a little acid, and that will give you the trans-diol. And so let's look at this. I mean, this is going to be a pretty simple step here. This is simply protonating oxygen and then having water come in and do a backside attack, which is similar to when the opening of your bromonium ion. So this part should be very, very easy for you to envision, but this is going to be a little bit harder. So let's look at all of this in a little bit more detail. So the first step is using a peroxy acid as a reagent, so to affect this reaction. There's a lot of things that we're going to have to discuss on this slide. So peroxyacetic acid. So you know what acetic acid is. You would be able to recognize that if we were missing one of the oxygens here. But when you have another oxygen inserted in there, like a peroxide, oxygen-oxygen bond means it's a peroxide. So this is like a peracid, because you have, instead of just OH, like if that's missing, you have OOH. So this is a peroxy acid. So this one is acetic. And so this is peroxyacetic acid. This one is used, it's fairly common. This peroxy acid is extremely common. And it's MCPBA. You will want to learn that abbreviation, MCPBA. You'll want to learn the name metachloroperbenzoic acid, metachloroperbenzoic acid. So you can see that this is a peracid, COOH. So there is your peracid right there. Metachloroperbenzoic acid. So this would be the benzoic acid here. So this is the metachloro, chloro in the meta position. You'll learn that when we discuss aryl compounds. And so up here you can see the way that this is turned around. The carbonyl, carbon, OOH. Here's the carbonyl, OOH. Carbonyl, OOH. And so this is simply rotated around. You've got the correct conformer here, so that this particular oxygen, the one that is bearing the proton, that's the reactive oxygen in this peracid. This one, the one that's bearing the hydrogen, is the one that is so reactive, and it is drawn closest to the double bond, because it's known that this is the exact oxygen that is inserted here and becomes part of the epoxide. So there have been studies done where that oxygen was labeled, and after the reaction takes place, the label is in the epoxide. So it's known that it's this oxygen. So this is the reaction mechanism that's drawn to explain all of this. And I'll just tell you that this is a very unusual reaction mechanism. Let me repeat that. This is very unusual. Normally in reaction mechanisms, in a single step, you might have one or 2 arrows, maybe 3, but almost never 4. And that's what we've got here going on, is 4 arrows. And so I don't think that you would ever be tested to be able to remember this mechanism because it's so busy. It's concerted. It's known that it's concerted. A lot of work has taken place to try to disprove this reaction mechanism. And they always wind up getting more and more evidence that supports that reaction mechanism. So, in a very concerted fashion, what happens is this hydrogen becomes attached to that carbonyl oxygen, and this pair of electrons moves over. So the carbonyl now is here instead of here. The carbonyl becomes here. You can see it. And so this hydrogen was originally over here. And this was originally the carbonyl. And so this oxygen becomes the epoxide oxygen. So you can see this is a 5-membered ring, and this is a 3-membered ring. So I don't think it's all that important for you to memorize this, but I hope that you'll become comfortable with it. You do need to know, as I said earlier, MCPBA, metachloroperbenzoic acid. This is a very common oxidizing reagent, and you will see it a lot in Org 2 as well. So you may as well learn it now. So the epoxide, once it's formed, is treated with water and some acid catalyst. So this is the hydronium ion. And so it protonates the epoxide. And then water is the nucleophile. I mean, if you remember, we saw this earlier. The exact same thing happened when you had bromine here, the bromonium ion. Now you have an oxonium ion. And so the exact same thing happened, and also when you had the mercuronium ion. So they're all very similar. The mechanisms are similar. Once you've seen this is the 3rd time you've seen the same mechanism. The only thing you're doing is changing the identity of that one atom. And so water comes in, does a SN2 attack, and then you deprotonate it. Now you've got the diol instead of the halohydrin, or instead of bromination. You've got the diol, and this is a trans diol. You had anti-attack. So it's the same thing that you've seen before, except you've just changed the identity of the onium ion. And note the similarities here. That's mercuronium, bromonium, and oxonium. All onium, onium, onium. Because in each case, they're bearing a positive charge, and they've increased their valence by 1. Very similar reactions. Now let's go on to the hydroxylation, the dihydroxylation. You can carry out this reaction and draw this mechanism using either osmium tetroxide or potassium permanganate. And the mechanisms are exactly the same. And so you can see the pair of electrons comes in, attacks oxygen, pair of electrons moves on to osmium. Now the pair of electrons moves out onto carbon. You've got a 5-membered ring, this cyclic 5-membered ring, and then you can react it with this weak base and get and protonate it, and you get the cis diol. This because it's a 5-membered ring, because it's adding across the double bond, it has to add from the same side. And so the two carbon-oxygen bonds must be formed on the same side. And so once here, again, they're on the same side, and they stay on the same side. So this is a cis-diol. The reaction takes place, syn addition. Okay? And let's see, N-methyl morpholino N-oxide, so NMO. I don't know that it's so important to know this name, except, you just need to know that this is used to affect the oxidation, or you can use, peroxide. So, in that way, you only have to use a catalytic amount of the osmium tetroxide, because osmium, it's a pollutant. You don't want to use that much of it, and it's expensive. So, now, potassium permanganate. So here it's the exact same mechanism, 5-membered ring. And once again, it has to be syn addition because it's added, both bonds are formed on the same side. You're going to have the cis-diol. So these two reactions are very, very similar, at least mechanistically. The reagents are totally different, but mechanistically, they're the same and the products are the same. So you can group them together in your mind, and it will make it easier to remember. And this is ozonolysis. And in ozonolysis, we're not going to really pay that much attention to the mechanisms. I think that the mechanism is covered in your textbook, but there is so much arguing over this mechanism by experts. I don't think that it's really that important for you to learn the mechanism, since it's disputed all the time, and there's no point in learning something if it's under dispute. That's my belief. So what you need to do is here just learn this is ozonolysis. Here's your ozone, dimethyl sulfoxide, and just learn that whenever you see this O3 and a double bond, the carbon-carbon double bond is going to be converted to 2 carbonyls. And so an easy way to look at it is to just think of it as cleaving right here, and you're going to put an oxygen on each end of that double bond. And so if you look at it, here is your original alkene, okay? Right there. And so you can just think of it as this has been inserted right there. And I don't think that you need to learn this mechanism. It's under dispute all the time. So just, learn the reaction. You don't have to pay that much attention to the mechanism. I don't think anyone would ever test you on something that experts are arguing about constantly. Predicting the products of addition reactions. So here we are. You've got a lot of addition reactions. So you have to analyze the reagents so that you'll know what it is that's going to be added across the double bond. You have to determine whether you're going to have Markovnikov or anti-Markovnikov addition. You have to determine whether you're going to have syn or anti. All of those different things to memorize. But if you group these together, like I have shown you in your preview review video, it will make it all so much easier. You have to look at the patterns. If you don't use the patterns, it's going to be 5 times harder. So let's say that you're going to do a 1-step synthesis. And you have to think about, keep in mind, what what sorts of additions, what sorts of reactions that you have as your tools. So you can do an addition reaction, you can do a substitution reaction, and you can do an elimination reaction. Those are really about the only three tools that you've got now. And so changing the position of a leaving group, if you wanted to do that. So can you move the bromine from the secondary to a tertiary carbon? Yes, you can. So you could do an elimination to get an alkene and then add it again, right? So you can do that. So, and you know how to put bromine onto a tertiary carbon, and you know how to do the elimination. So here, to do the elimination, you need to use the base. You need to use sodium methoxide, not T-butoxy, the T-butoxide, because you want something that's non-bulky so you can get this more highly substituted alkene, because you're going to have to put the bromine in here. So now let's look at what you've got. So you're going to use the less bulky base so that you can get the more highly substituted alkene, and then you're going to use the Markovnikov addition of H and Br, hydrogen bromide addition. Okay, and so this is going to be the answer to the solution to that problem. And you can change the position of a pi bond also. So here you're going from a more highly substituted alkene to a less highly substituted alkene. So you can do addition, add HBr across anti-Markovnikov of hydrogen and bromine. And then you can do the elimination to give the Hoffman product, the less highly substituted alkene. So remember that if you use HBr and peroxides, you will get the anti-Markovnikov addition. And then to use the bulky base, you will get the elimination to give you the less highly substituted alkene. And so here, finally, this is a review of all the addition reactions that you've had. Go back and review that very first video that I made for you, the preview video, where I showed you the similarities. What you'll see is this where I've drawn circles around these, showing you the ones that are similar. These two are similar. These are similar. And by making use of that, you will be able to learn them so much more easily. It's chunking, remember, and you'll be able to learn the groups. Instead of having 10 individual reactions, you'll just have about maybe 5 different groups. So that is the end of Chapter 8.